Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, as you know that we have started a series on polynuclear hydrocarbons and heterocyclic compound, and today we are conducting yet another lecture in the same series. In today's lecture we will try and understand a hydrocarbon called phenanthrene. We will try to understand its structure, its properties and its derivatives. To discuss the topic, we have with us our subject expert, Dr. Sushila Singhal. Dr. Singhal is Assistant Professor in Department of Chemistry in Deshbandhu College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. Thanks for the nice words, Amritji. Good day to all viewers. Today in the series of polynuclear hydrocarbons and heterocyclic compounds, we are here to discuss about the hydrocarbon phenanthrene. This phenanthrene is a polynuclear hydrocarbon. In this series, we already have discussed naphthalene and anthracene also. This is the third family member of this polynuclear hydrocarbon. These are having the carcinogenic properties. Carcinogenic compounds are those compounds which causes cancers. Those hydrocarbons which contain benzene rings in them, they causes cancer. But with this property, these are having some pharmaceutical applications also. These can be used against this cancer, can be used as anti-tumor agents, antimicrobial activities and antioxidants also. So phenanthrene is one of this hydrocarbon. So today in this lecture we will discuss about this phenanthrene molecule, its preparation. Its preparation is of many name reactions. One of them is Hayward synthesis, then Nord synthesis, stop condensation from biphenyl methyl phenanthrene. Then in the second part of this lecture, we will study about the physical property of phenanthrene and the chemical properties of the phenanthrene. In the chemical properties, since it is a aromatic hydrocarbon, it will undergo electrophilic substitution reactions like nitration, sulfonation, alkylation and chloromethylation also. Further, then it will undergo addition reactions which will include oxidation and reduction reactions. Then we will study about phenanthrene derivatives, which will include its oxidative products and the reduction products, which include phenanthroquinoline, phenanthrol, etc. And then we will study the application of this phenanthrene molecule. So first of all, we will start with its introduction. Phenanthrene is a polynuclear hydrocarbons. These polynuclear hydrocarbons can contain benzene ring which are called benzenoids, and they may not contain benzene ring which are called non-benzenoid compounds. In case of benzenoid compounds, we can have isolated rings and we can have fused rings. In case of isolated rings, you can say here the example of biphenyl, where two benzene rings are separated by a covalent bond. While in case of fused rings, we are having naphthalene and phenanthrene. Naphthalene is a linear hydrocarbon, while phenanthrene is having the one benzene ring angular to the two benzene rings which are linear at their position. In case of non-benzenoid, we can see the example of azulenes. So today we will study this angular example of this polynuclear hydrocarbon. This is the phenanthrene molecule. You can see the ball stick model in which you can see the carbon and the hydrogens, and these dotted lines for the delocalized pi electrons. The molecular formula of this phenanthrene hydrocarbon is C14H10. Since it contains only carbon and hydrogen, so it is a hydrocarbon. It doesn't have any heteroatom. And these three benzene rings, they are fused at the ortho carbons. Ortho position means 1-2 position of these two carbons. So this is the ortho position, and the third benzene ring is again at the ortho position, which is angular to the first two rings. This phenanthrene, this we can get from the nature, from the coal tar and from the mineral, which is a revetite mineral. From the coal tar distillation, we get this phenanthrene molecule along with the anthracene. So it is having the same properties, similar properties with respect to the anthracene. All carbons are sp2 hybridized in phenanthrene. Since we get phenanthrene along with the anthracene, so we have to separate these two. So in case of isolation of phenanthrene, we get this phenanthrene from the green oil fraction of the coal tar, which on cooling this fraction we get a solid mass which contains phenanthrene, anthracene and carbazole. Treatment of this fraction, this solid mass with the naphtha solvent, we get phenanthrene in the dissolved form. After getting this dissolved form, we evaporate this solution and we will get the crude phenanthrene, which further can be purified by recrystallization of the picrates from the ethanol, and we will get here the pure phenanthrene. Then comes the nomenclature of phenanthrene. Phenanthrene hydrocarbon contains 5 types of hydrogens. So it is having the 5 different positions. This is the phenanthrene molecule. This is the carbon number 1, 2, 3, 4, and then we will move to the third ring, then 5, 6, 7 and 8. This ring which is in the center, this will get the carbon number 9 and the 10. So this is the nomenclature of hydrogen present in this hydrocarbon. This can also be designated as alpha, beta, gamma, omega and epsilon hydrogens. The hydrogens which are identical at the first position and the 8 positions are alpha, then at the 2 and the 7 positions are beta, at the position number 3 and 6 are gamma, position number 4 and 5 are called omega, and the rest 2 are called epsilon hydrogens. In naming the derivative of phenanthrene, the position of the substituent can be indicated by the numbers only. And the first structure, this is mainly used in all the reactions to designate the position of the substituent. Then comes the isomerism in phenanthrene. Phenanthrene is an isomer of anthracene. The only difference is in the its position, that in anthracene we are having the 3 benzene rings in the linear position, while in the phenanthrene we are having the third ring is angular to the first 2 rings. Phenanthrene forms 5 different mono-substituted compounds. So we can have 5 different isomers which are position isomers, while if we do the di substitution in phenanthrene, we will get 25 different isomers. Then comes a molecular orbital structure of phenanthrene. Since phenanthrene is a hydrocarbon which contains all carbons with the double bond, so all carbon are sp2 hybridized, and the sp2 hybrid orbitals, they overlap with each other and with the s orbital of the 10 hydrogen atoms, forming carbon-carbon single bond and carbon-hydrogen single bond, which is called the sigma bonds. These sigma bond result from the overlap of the trigonal sp2 orbitals. So all carbon and hydrogen atoms, they lie in the same plane. That's why this molecule is planar, and which has been confirmed by its X-ray diffraction studies. Further, the sideways overlapping of the unhybridized pz orbital which is left, that produces a pi molecular orbital above and below the plane, forming the delocalized pi electrons. Further, this phenanthrene, it is an aromatic compound, so it should follow the aromaticity criteria. One of them is Huckel's rule, which is 4n plus 2 pi electrons. By calculating this 4n plus 2, we will get here the n will be equal to 1, which is an integer, which confirms that this phenanthrene is aromatic in nature. Here you can see the molecular orbital picture of the phenanthrene molecules. These are the 3 rings, and these are the pz unhybridized orbitals, which on sideways overlapping will form these pi molecular orbital, which are delocalized pi electron cloud. So on this molecular orbital structure, we can write the shorthand representation of phenanthrene like these 3 rings with the spheres in them. This is the easiest form of representation of phenanthrene. Then comes the structure determination of phenanthrene. In case of structure determination, the first step is the molecular formula designation. So for the molecular formula, we have to do the elemental analysis that which elements are present in a particular hydrocarbon or a particular compound. So in case of phenanthrene, we get that it contains only carbon and hydrogen. Carbon is the 14 and 10 and hydrogen is the 10. So its molecular mass determination comes to be C14H10. Then many functional group analysis has been done on this phenanthrene, and we will get that it doesn't contain any functional group which confirms that it is a hydrocarbon. Since it is a hydrocarbon, then we have to do many reactions on this particular hydrocarbon. One of them is oxidation reduction reaction. So in case of oxidation reaction, phenanthrene on oxidation with chromic acid gives phenanthraquinol, which on further oxidation with hydrogen peroxide will give us a diphennic acid. This is a diphennic acid. You can see here two carboxylic groups at the ortho positions, which further on reaction with alkali in the presence of calcium oxide will give us the diphenyl compound. This reaction confirms that phenanthrene and phenanthraquinone, whose structure we don't know, should have these two rings, at least these two benzene rings together with the covalent bond in between them. So from this oxidation reaction, we can see that the basic skeleton of the phenanthrone should be indicated by this structure by the formation of diphenyl and these two hydrogens at the ortho position. Now if we compare this with the molecular formula, we will be left with the two hydrogens only. So to compensate these two hydrogens, we can draw this structure in which these two hydrogens has been compensated here. So for this phenanthrene, we can draw this structure in which this ring is angular to the first two ring, and this structure of phenanthrene is further confirmed by its synthesis. Then comes a resonance in phenanthrene. Since phenanthrene is a heterocyclic compound, is a aromatic hydrocarbon, it is also resonance hybrid of the following contributing structures. So 5 resonating structures can be drawn. Its resonance energy is about 387 kilojoule per mole, and you can see in the structures that in most of the structures we are having at least 2 benzene rings intact. So the structures which are having 2 benzene rings are more stabilized and will contribute more towards the hybrid of the phenanthrene. Now comes the synthesis of phenanthrene. The first one is Haworth synthesis. It involves 5 steps. In first step, naphthalene is taken as the precursor and it is reacted with the succinic anhydride. It undergoes acylation, which is called Friedel-Crafts acylation. So these two molecules are heated in the presence of aluminium chloride, which in this molecule, this succinic anhydride will break from this position and it will attach to the naphthalene ring, forming the alpha naphthoyl propanoic acid. This attachment is at the alpha position of the naphthalene molecule, so it is called alpha naphthoyl propanoic acid. In the step 2, this alpha naphthoyl propanoic acid will undergo Clemmensen reduction in the presence of zinc amalgam and hydrochloric acid to give us the gamma naphthyl butyric acid. This product, by this reduction, we will get here this butyric acid, and at the gamma position of this butyric acid we are having this naphthalene ring, so it is gamma naphthyl butyric acid. In the third step, this gamma naphthyl butyric acid will undergo ring closure reaction in the presence of concentrated sulfuric acid or polyphosphoric acid to give us 1 keto 1 2 3 4 tetraketophenanthrene, and water will go out. Since cyclization will take place in the presence of sulfuric acid, this ring will complete from this side. In the step 4, the product from the step 3 will further undergo Clemenza reduction in the same manner with the zinc amalgam in the presence of hydrochloric acid to give us 1 2 3 4 tetrahydrophenanthrene, which in the last step will undergo aromatization or oxidation, in which this is heated with palladium to yield us the phenanthrene molecule. So, starting from the naphthalene with the 5 steps of named reactions, we will get here the phenanthrene in the last step. Then comes the Nor synthesis. It is carried out by heating orthonitrobenzaldehyde with sodium beta phenyl acetate in the presence of acetic anhydride, which upon reduction and diazotization will first give us the salt, and this salt on treatment with sulfuric acid and copper powder will give us the carboxylic acid, which upon heating will further give us the phenanthrene. You can see in the reaction we have taken here the orthonitrobenzaldehyde. This is orthonitrobenzaldehyde, and this is the phenyl sodium phenyl acetate molecule in the presence of acetic anhydride. First will undergo condensation at this position, which on reduction in the presence of tin and hydrochloric acid, followed by diazotization with sodium nitrite in the presence of acidic medium, will form this salt. This is the diazonium salt, which in the presence of copper and sulfuric acid will undergo cyclization to form this ring closure. This carboxylic acid group will decarboxylate in the last step on heating, and we will get here the final product, which is called phenanthrene. Phenanthrene can also be obtained by passing dibenzyl through a red hot tube. This is a dibenzyl in which we are having these two benzene ring. It will undergo dehydrogenation on heating, and we will get here this cyclized product, which is called phenanthrene. Phenanthrene can also be obtained by cyclodehydrogenation of 2,2-dimethyl diphenyl using sulfur. Sulfur is also a reagent which can be used in the cyclization processes. So, this is the molecule, this is the 2,2-dimethyl diphenyl hydrocarbon, which on reaction with sulfur will undergo dehydrogenation to give us this phenanthrene molecule. One of the most important reaction of phenanthrene synthesis is Bogert-Cook synthesis, in which we have to take these two ingredients. One of them is beta phenyl ethyl. This is beta phenyl ethyl magnesium bromide along with cyclohexanone. These two molecules will undergo condensation to give us this adduct, which on reaction with sulfuric acid first will undergo dehydration. Here dehydration will take place. This is an unstable molecule which then undergoes cyclization, immediate cyclization, since the previous molecule is unstable, will give us this molecule which is a reduced phenanthrene ring, will oxidize on heating to give us the phenanthrene molecule. Then comes the Bardhan-Sengupta synthesis. This Bardhan-Sengupta synthesis, for the synthesis of phenanthrene, we have to take two ingredients. One of them is beta phenyl ethyl bromide and one is 2-carboxycyclohexanone. First we have to prepare these two ingredients itself, then we will condense these together to form the phenanthrene. So, this process involves the electrophilic aromatic substitution using a tethered cyclohexanol group using phosphorus pentaoxide, which closes the central ring onto an existing aromatic ring. Dehydrogenation using selenium converts the other rings to aromatic ones. So, first of all we have to prepare this beta phenyl ethyl bromide from the bromobenzene. Bromobenzene first will form this Grignard reagent. This is phenyl magnesium bromide on reaction with magnesium in the presence of ether volatile solvent. Then it will react with this oxyrane or cyclic ether and further undergo hydrolysis to give us beta phenyl ethyl alcohol, which on further reaction with hydrogen bromide substitution will take place at this position. Hydroxy group will undergo substitution with the bromide and we will get here beta phenyl ethyl bromide. So, we are getting here the first ingredients. The second ingredient is 2-carboethoxy cyclohexanol, which we can prepare from cyclohexanol on reaction with diethyl oxalate. This is the diethyl, 2 ethyl groups are there on the oxalic acid. So, this is called diethyl oxalate. In the presence of sodium ethoxide, we will get alpha keto ester. This is the alpha keto ester, which on heating will undergo decarbonylation. One carbon is reducing from this beta keto ester and we are getting here 2-carboethoxy cyclohexanol. Now, these first and the second reaction products will condense together. This is the first and this is the second. These will undergo condensation to give us this adduct, which on further reaction with first with the alkali and then with the hydrochloric acid followed by heating will give us this adduct which is having a ketonic group, which undergo first enolization, then in the presence of phosphorus pentaoxide on heating it will undergo cyclization at this position and we will get here a reduced phenanthrene ring, which on oxidation followed by heating will give us the phenanthrene ring. We can prepare phenanthrene from 2-bromonaphthalene 1-carbaldehyde molecule also. So, for this we have to take 2-bromonaphthalene 1-carbaldehyde. This is the 2-bromonaphthalene 2-carbaldehyde, which on reaction with 1-bromo-2-propane, this is 1-bromo-2-propane molecule in the presence of DMF solvent, first will undergo extension of the ring, which further react with the sodium hydride, again react with 1-bromo-2-propane and it will extend the ring like this, forming the dialylated compound, which through the metathesis reaction will undergo cyclization followed by subsequent treatment with palladium 2 acetate, which will do the oxidation reaction to give us the phenanthrene molecule. So, here the ring closure will take place from this position and on oxidation we will get here the phenanthrene molecule. Then comes the Fittig reaction. Fittig reaction is a well known name reaction in which we take the hydrocarbons along with the sodium metal. So, here we have taken the aromatic hydrocarbon. In this case we have taken orthobromobenzyl bromide. 2 molecules of this orthobromobenzyl bromide has been taken along with the sodium metal and sodium bromide will go out as a side product, condensing these 2 hydrocarbon to give us this cyclized product, which will further undergo oxidation to give us phenanthrene hydrocarbon. This phenanthrene can also be prepared by the irradiation method, by the UV radiation, by the microwave irradiation, and in this case we can take stilbene cis, either cis or either trans. We can take this cis or trans-stilbene, which on irradiation with microwave radiations, which cyclizes this molecule to give us the phenanthrene hydrocarbon. So, we can do these microwave reactions also, which are greener in method, in which we do not have to add any solvent. So, these reactions are green, and atomization is also done in these type of reactions. Then comes the stop condensation. This is also the most important reaction of phenanthrene preparation. In this reaction, we can take any aromatic aldehyde. Here we have taken acetophenone. When it reacts with succinic ester, it first undergoes condensation to give us this product, which is having an extension on the position number 2 of the naphthalene ring of the acetophenone aromatic carbon. In this carbon, first it will undergo forming this cyclic ether, which on reaction with alkali followed by reaction with hydrogen will give us the hydrolysis product, in which we will get here the carboxylic acid group, which on further reaction with hydrogen fluoride cyclizes itself to give us a reduced substituted phenanthrene ring, which on oxidation will give us the phenanthrene molecule, which is having substitution of methyl group at the position number 1. So, we will get here the final product 1-methyl phenanthrene. We can also prepare the substituted phenanthrene also. In the first reaction, in the Haworth synthesis preparation of the phenanthrene, one of the intermediate product we have got this product. At that stage also we can do the reaction with the Grignard reagent in the Haworth synthesis, when this product on reaction with RMGX, this is a Grignard reagent, followed by hydrolysis will give us the hydroxy groups introduced in the ingredient, which on oxidation will give us the 1-alkyl phenanthrene hydrocarbon. We can also prepare 2-alkyl phenanthrene. We can also do the substitution at the 2-alkyl position. In this we have taken the naphthalene molecule along with the succinic anhydride. In the presence of aluminium chloride, we will get here the adduct in which succinic anhydride is attached at the carbon number 1. Since we have already taken the alkyl part in the succinic anhydride, so we will this reaction is almost same as that of Haworth synthesis, and in this reaction the final product we will get this methyl or this alkyl part at the carbon number 2, and we will get here the 2-alkyl phenanthrene. So, this was all about the preparations of phenanthrene. This phenanthrene, this carcinogenic hydrocarbon, which we can prepare from many named reactions, is very important hydrocarbon. So, this was all about the preparation part of phenanthrene. Thank you. So, after preparations, now we will start with the physical property of the phenanthrene hydrocarbon. Phenanthrene hydrocarbon is a colorless crystalline molecule which is shining in nature. It is glistering flakes. It is white in color, or you can say it is colorless. It forms fluorescent color with the benzene ring. So, it is a fluorescent, it shows fluorescence reaction. Its melting point is 101 degree centigrade. It is insoluble in water, but it is soluble in many organic solvents, especially alcohol, ether and benzene. It is highly volatile and it sublimes on heating like naphthalene hydrocarbon. Then comes its chemical properties. In case of chemical properties, since it is a aromatic hydrocarbon like benzene, naphthalene and anthracene, it also undergoes electrophilic aromatic substitution reaction. Now the question comes that this electrophilic substitution takes place at which position? Out of the all 10 hydrogens, which hydrogens are more easily substituted in case of phenanthrenes? So here position number 9 and 10 are more easily substituted. Why it happens? It happens because of the resonance stabilized structures formed in the reaction, in the mechanism of the reaction when the electrophile attacks on this phenanthrene molecule. So we can see from the mechanism that first of all we will generate the electrophile. Now this electrophile, if it attacks at the position number 9, here this is the bond. This bond will shift at the position number 9. Now it will become the electron rich position, and electrophile will attack on this position and we will get this intermediate ion. This intermediate ion is a resonance stabilized structure. Since in this the resonating structures which we can draw will have the maximum number of 5 resonating structures can be drawn, and out of them 3 structures are there in which 2 benzene rings are intact. So more the number of benzene ring intact in the resonance stabilized structures, more these structures will contribute to the resonance hybrid, and more will be the stability of the resonance hybrid. More the stability of the resonance hybrid, lesser will be the resonance energy, and more will be its ease to undergo substitution. So in case of phenanthrene, the position number 9 is more easily substituted since the resonance structures are more stable. It can also undergo addition reactions at the position number 9 and 10, and if it comes here, then this nucleophile can also attack at this position number 10, since it is now electron deficient position. As you can see that when electron will shift at the position number 9, it makes the position number 9 electron rich and position number 10 electron deficient. So nucleophile can also attack on this phenanthrene, and we can also get here the addition product as well as the substituted product. Substituted product, if this position number 9 is already occupied, then we will get the further substitution on the position number 10. Now here are the few electrophilic substitution reaction. One of them is halogenation. Phenanthrene on reaction with halogen, here we have taken the chlorine. In the presence of carbon tetrachloride, first it will form the addition product. This chlorine molecule, it will generate a electrophile as well as a nucleophile simultaneously, and both will attack on this phenanthrene to give us this addition product. This is the 9,10 dichloro 9,10 dihydrophenanthrene, which on heating will lose the one hydrochloride, and we will get here the only one chlorine at the position number 9. The final product we are getting is the substituted product. So it is a substitution reaction. Same as that of chlorination, bromination can also be done, but this bromination, this requires ferric salt yielding the bromination at the carbon number 9, and we will get here this 9-bromophenanthrene. This 9-bromophenanthrene, this is a very important compound. Since this compound can be used in the many preparations also, we can use this 9-bromophenanthrene on undergo cyanidation with the copper cyanide to give us 9-cyano derivative, which followed by hydrolysis will give us the 9-carboxylic derivative, and these derivative we can use in the pharmaceutical properties. It can undergo nitration also. Phenanthrene on nitration with the nitrating mixture, which is nitric acid in the presence of concentrated sulfuric acid, will give us the 9-nitrophenanthrene. So, here also the substitution will take place at the carbon number 9, and we will get here the 9 substituted phenanthrene product. Then comes the sulfonation. In case of sulfonation, phenanthrene on reaction with sulfuric acid, we do not get the substituted product at the carbon number 9. We get here a mixture of 2 sulfonic acid, one of them is 2-phenanthrene sulfonic acid and one of them is 3-phenanthrene sulfonic acid at temperature 120 degrees centigrade. This is because of these sulfonic acid bulky groups, so steric hindrance takes place here, and instead of getting the 9 substituted product, we are getting a mixture here. Phenanthrene can further undergo Friedel-Crafts acylation on reaction with acetyl chloride. Phenanthrene, this is the acetyl chloride, in the presence of aluminium chloride at 0 degrees centigrade will give us a 9-acetyl phenanthrene hydrocarbon. Here also the substitution of the acetyl group takes place at the carbon number 9. Then comes the chloromethylation. In case of chloromethylation, we are here adding the 1 aldehyde group here in the phenanthrene ring. We are introducing this aldehyde group to the phenanthrene. Here also the substitution will take place at the position number 9, and we will get here the 9-carboxyphenanthrene. Then comes the reduction reaction of phenanthrene. This is a type of addition reaction in which we can add hydrogens to the phenanthrene ring. The reduction of this phenanthrene is carried out in the presence of mixture of sodium and amyl alcohol or copper oxide with the chromic oxide mixture. Here we can add the hydrogens at the carbon number 9. Here we are getting the carbon number 9 and 10. At these two positions we are adding the hydrogens. So, we are getting here the 9,10 dihydrophenanthrene addition product. Then comes the oxidation reaction of phenanthrene. Oxidation of phenanthrene can be carried out with various reagent. One of them is the acidified dichromate, which on reaction with phenanthrene forms the 9,10 phenanthroquinone product, which is very useful product, which is having many application in the pharmaceutical industries, in the metallocene industries. Phenanthrene can also be oxidized using ozone. When phenanthrene reacts with ozone, first it forms this ozonide, this is the monoozonide, which on reaction with KMnO4 will give us a diphenic acid. This is the diphenic acid, this is the oxidized product of phenanthrene. This diphenic acid, this can also be prepared directly from the phenanthrene by its direct oxidation with the H2O2, hydrogen peroxide. On reaction with phenanthrene will give directly diphenic acid. So, we can get many oxidation products with using different oxidizing reagents. Steps may be different via using the different reagents, but the final product we are getting oxidation products are diphenic acid and the phenanthrene quinolone. Since it is a hydrocarbon, it undergoes picrate formation also. Picrate formation is the formation in which we take the hydrocarbon on reaction with picric acid. either in the alcohol or in the benzene medium. First we will prepare the solvents of both separately, phenanthrene with alcohol or with benzene, and picric acid in the separate test tube with alcohol or benzene. Then we will mix these together, and which on heating will form the picrates. The color of the picrate then finally decide that the given product is whether phenanthrene or any other hydrocarbon. So it is a test reaction of the hydrocarbon also. In this reaction, phenanthrene is the electron rich molecule, and picric acid, since it is containing the 3 nitro groups, it is very electron deficient. Nitro groups are electron withdrawing groups which withdraws electron from the benzene ring. So this electron withdrawing nature of nitro groups on the picric acid will makes a picrate formation with this electron rich phenanthrene ring. So we will get here the phenanthrene picrates. Now comes the phenanthrene derivatives. Phenanthrene derivatives can be phenanthraquinone, which is its oxidized product. It is orange solid. Here we can get this phenanthraquinone on oxidation with acidified dichromate. This dicarbonylated compound, this dicarbonylated derivative of phenanthrene, it is having many type of chemical reactions of many importance in organic synthesis, especially in electrophilic aromatic substitution and many condensation reactions, being an excellent starting material to prepare relatively simple and bioactive substances. This 9,10 phenanthraquinone, this can also be synthesized radiating through a mercury vapor lamp from 2,2-diphenyl dicarboxyaldehyde. This is the molecule in which we are having 2 aldehyde group at the 2 and 2- positions. It undergoes oxidation in the presence of radiations, in the presence of sunlight, and we can get here this phenanthraquinone derivative. We can prepare this phenanthraquinone using different solvent. Here in this reaction, acetone has been taken as a solvent and the benzoyl peroxide, which on refluxing about 72 hours give us the derivative, will give us this final product. This 9,10 phenanthraquinone, this can also be prepared from the 9-methyl phenanthrene on reaction with carbon tetrachloride using chromium chloride solvent, and we can get here this phenanthrene derivative. What is the use of this phenanthraquinone? This phenanthraquinone can further undergo many rearrangements using different solvents, will give us some important compounds which are having many pharmacological activities. Here you can see in this reaction then that this phenanthraquinone on reaction with alkali, from where we are getting these hydroxide ions, these react on this dicarbonyl part of phenanthraquinone, will give us this adduct in which it undergoes benzylic acid type of rearrangement, and this medium ring, this is the centered ring, this undergoes ring contraction. This 6-membered ring, this rearranges itself to form the 5-membered ring. This type of rearrangement is called benzylic acid type rearrangement. From this we get here the 9-hydroxyfluorine 9-carboxylic acid. This intermediate product, which is having the carboxylic acid group and the hydroxy group at the same carbon, will first undergo decarboxylation to give us fluorinone, which on oxidation with chromium oxide in the presence of pyridine first form the ketonic group, the dicarbonyl compound in the centered ring, which is called the fluorinone, which on Clemmensen reduction on reaction with zinc amalgam in the presence of concentrated hydrochloric acid will give us the final hydrocarbon, which is called the fluorine. So, from phenanthroquinone, using different type of rearrangement in the different solvent, we can get the final product, which is having many applications. While this phenanthroquinone, if we reduced this product using sulfurous acid, now we have taken here the sulfuric acid and we have reduced this phenanthrene derivative. Here first these two dicarbonyl part of this phenanthroquinone, these two carbonyl groups will undergo reduction to form the secondary alcohol. Here we are getting 9,10-diol, which on hydrolysis will undergo pinacol-pinacolone type of rearrangement. In this type of rearrangement, first hydrolysis will take place at 9,10-diol carbons. One of this diol hydroxy group will undergo hydrolysis to form this water moiety, which will go out as a side product, and this again this 6-membered centered ring will rearrange itself to form the 5-membered ring in the center, and then we will get here the final product fluorinone. So, using the different solvents and the different type of reaction, whether we are using here the reduction or the oxidation, we can get the different type of rearrangements. Then comes the one of most important phenanthrene derivative, which is called phenanthroline. Here in this phenanthroline, we are having 2 nitrogen heteroatoms in this polycyclic hydrocarbon. The position of these nitrogen can be different. We can get different type of phenanthrene derivative at the carbon number. If this nitrogen present at carbon number 1 and 7, then it will be 1,7 phenanthroline. It can be 1,10 in phenanthroline. It can be 4,7 phenanthroline, and likewise we can change this position of nitrogen at different position and we can get here the subsequent derivative. Now, what is the application of these phenanthroline which contains this heteroatom? It is used in the metallocene industries. It is used as a ligand since it binds the metal tightly. Many homoleptic complexes like ferrone can be generated, which is used in the photometric determination of ferrous ions. It is used as a redox indicator having the standard potential positive 1.06 volt. The reduced ferrous forms a deep red coloration and the oxidized form is the light blue coloration. It can also be used as an indicator for alkyl lithium reagent as they form deeply colored derivative with phenanthroline. The alkyl lithium content of solution can be determined by treatment of such reagents with small amount of phenanthroline followed by titration with alcohol to the colorless end point. Then next phenanthrene derivatives comes phenanthrol, in which we are having the hydroxy groups at the phenanthrene molecule. Again this hydroxy group can be present at any hydrogen. If it present at the carbon number 1, it is 1 phenanthrol. It can be at the 2 position number, so it will be 2 phenanthrol. Here we have shown you the 1 phenanthrol and the 9 phenanthrol. The 1-hydroxyphenanthrene or phenanthrol is a human metabolite which is detected in the urine of persons which are exposed to these polycyclic aromatic hydrocarbon. It is a pollutant also which can be marked in marine fishes bile juices. It exerts cardioprotective effects against ischemia, reperfusion injuries, and it reduces the stroke injuries, and it bears many such clinical applications. So, these phenanthrol can be studied in the pharmacological applications. Besides this phenanthrene molecule, it itself contains many biological activities. Although it is a carcinogenic hydrocarbon, but still it has many anti-cancer activity. Here you can see in this compound A, which is formed from the condensation of this 9,10-phenanthroquinone. This is the part of 9,10-phenanthroquinone derivative, and this half part is the trans 1,2-diaminocyclohexane. When these two condenses together, the condensed product, this condensed product fight against the cancer disease, so it presented an anti-leukemic activity. Likewise, in the compound B also, this is the compound B. Here also this is the part of phenanthrene quinone, and this second half part is the thiosemicarbazone. This condensation product of phenanthroquinone, this also shows the anti-cancer properties. This phenanthrene molecule, this phenanthrene derivatives, it also shows antimicrobial activities against E. coli, against Salmonella typhi and Staphylococcus aureus. From this complex formation, here you can see then in this complex which is formed from the anthraquinone, here these are the two anthraquinone part, which on reaction with vanadium sulfate forms this complex, which is a sulfate. It is a binder, this vanadium and acetonitrile solution, which binds these two moieties together using this ligand, forms this product which shows antimicrobial activity. One of the natural product, that is called tensionone, it can also be prepared from phenanthrene. It also has many strong antioxidant activities. It against the reduced lipid peroxidation. This is the molecule which is tensionone. It also contains this phenanthrene part. So it can be obtained, it can be synthesized from the phenanthrene using many substitution reaction like alkylation. Here also alkylation and ring extension has been taken place. So these natural products which contains the phenanthrene type of skeleton can also be prepared from the phenanthrene. Then comes the phenanthrene application. Phenanthrene itself can produce phenanthroquinone, polyester resin, alkyl resin and benzene anhydride. These products, these derivative itself have many application in the organic synthesis. These are used as many solvents. These are used in many ingredient of many synthesis products. These are commercially used products. Phenanthrene is also very important skeleton nucleus in the bile acids, in the bile juices, in the sex hormones and the cardiac glycosides also. Further, this phenanthrene is having the industrial application, like in the paper making, it is used as the anti-fogging agent of the pulp. In the dye industry, it can be used as 2-amino-phenanthroquinone and benzanthrone, and in the preparation of sulfur wet dyes. Phenanthrene is also having the application in the pharmacology, in the medicine industries, where it can produce alkaloid. Many of the alkaloid have this phenanthrene skeletal nucleus, like codeine, which is used as analgesic and cough suppressant. Now what is this analgesic? How this phenanthrene is used in these analgesic properties? These analgesic properties are the pain reducing properties of phenanthrene molecule. This phenanthrene can be used, its derivative can be used in the analgesic property, where on application on the skin, or you can say outside application, it reduces the pain, so it is an analgesic, and it is also the cough suppressant. In case of alkaloid, alkaloid can be used in the suppression of the cough, in which we are getting the fat, we are getting the lipid in the body which gets stored. So, by the oxidation of that lipid, since we have used the application in the lipid reduction, lipid oxidation, so from that part of this application it can be used as the cough suppressant. This phenanthrene can also be used for the production of fuel of jet plane. Now you can see that this phenanthrene also this is a carcinogenic product. The study on this phenanthrene is not that easy, but it is very important as the point of medicine industry, from the point of dyes industry, as it can also be used in the fuel. So research on this compound should be go on by precautions, with precautions, and this phenanthrene can be studied further. Now comes the few questions based on today's lecture, that how this phenanthrene can be synthesized from naphthalene. This can also be synthesized from the benzene, so we can also outline the preparation from the benzene starting material. We can give some Haworth synthesis of phenanthrene, Knorr synthesis of phenanthrene, and how we can convert this phenanthrene into diphenic acid. This phenanthrene can be isolated from anthracene, and we can see that substitution in the phenanthrene takes place at position number 9. So it can be compared from its resonating structures. So we can do the resonating part of phenanthrene molecule in this question. Many conversions can be made from many oxidation and reduction reactions and electrophilic substitution reactions. So we can convert phenanthrene into 9-bromophenanthrene. Then from the application part, phenanthrene can be converted into polynuclear hydrocarbon fluorinone via different arrangements using different solvents like benzylic rearrangement, and it can undergo pinacol-pinacolone rearrangement. Then comes the question of its derivative, that how the phenanthrene derivatives can be prepared from the phenanthrene, which can be prepared from the oxidation reactions, which can be prepared by diol preparations, and then comes its application part. So this was all about the phenanthrene molecule. This is the most important hydrocarbon. One of the extended hydrocarbon is also there, in which we are having the 4 rings together condensed, which is called the chrysene hydrocarbon, which is the higher member of this phenanthrene molecule. We can also study the electrophilic substitution reactions in that molecule also, and many application part of that phenanthrene. So this was all about the polynuclear hydrocarbons. Thank you.
Dear friends, we hope that with today's lecture you have come to understand what polynuclear hydrocarbons are all about, and especially the phenanthrene polynuclear hydrocarbon that we were discussing about. With that, we want to thank Dr. Singhal for this wonderful lecture, and thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.